Oh, hello everybody. Thank you for coming. I'm Simon Parker. I'm going to talk a little bit today about signal analysis 2. Leading on from where Simon Gray left off in the last session. Perhaps one of the things I want to start by saying is that if you're using Signal by default, it will be the time units will all be set to seconds. And most of you, I suspect, will be using milliseconds. So if you go into the preferences, we can say show time as milliseconds is probably the most convenient for you. Having done that, if I now open a file, you can see the x-axis is now in milliseconds, which is much more convenient to work with. If I look at, I think Simon Gray got on to talking about some of the new memory views you can create. You did talk about the waveform average. Mentioned that these other memory views we can create. I look at the auto average. This is essentially, it's very similar, but it produces multiple averages. So the upper part of the dialog here is the same as before. And if we look initially at the standard method for auto averaging, we can put an upper limit on how many averages we do. And then we have the frames per average and the frames between averages. Frames between averages is the number of frames that you step forward from the start of one average to the start of the next. So it is possible to have averages that overlap in that respect. Here by default, we're just averaging 2 frames, whereby and stepping forward 2 frames, so the frames are not actually overlapping. And this should produce a file, a memory view with half the number of frames in it as the original file. Now, when you're processing averages, you can specify, for instance, that you want to exclude tagged frames, which immediately begs the question, when you're counting your frames per average, and your frames between averages, do the tagged frames count as being part of that number of frames in the average, even if it's being excluded? Now, it may be important to you that you have at least 2 frames in your average, or it may be more important to stay in sync with whatever stimuli you're giving, in which case you would click on count excluded frames. So now your averages may only contain, for instance, 1 frame from the source instead of 2 frames, but they will stay in sync with the original stimuli, which might be important to you. You see our raw data here starts at minus 10 milliseconds. We may or may not want the average to start at minus 10 milliseconds. If we do, then we will say average x-axis starts at 0. We want to push that back and make that now 0, or leave that unchecked if you want 0 time to be back in the middle of your data sweep, as we have here. That usually corresponds to some stimulus you're giving, and you might want to keep that. And obviously, do we want the mean of the data, or do we want the total? Using the total error bars, maybe of interest to you. If I do click that new, standard method of selecting the frames we want to process. By default, we've got all frames, and then we have a frames subset. This allows us to be more specific about which frames we want to include. As you say, only the tagged frames or only the untagged frames, for instance, or frames of a particular state. So if I process that, and you see we now have a memory view with multiple frames in it, corresponding to the averages that are being built up. or the memory options. Amplitude histogram, this is going to be used mainly for single channel data. If I look at the single channel file, you can see how data tends to hang around at particular levels in single channel data. And what we will want is produce a histogram that shows how long the data is spending at a particular level. So if I do amplitude histogram of that data, we're going to analyze the whole file, so mean time to max time. And we wanted to look at the range of the y-axis. This is going to be the range of the histogram. So what is y high on the original data is going to be the extreme right-hand end of the x-axis. For those of you not doing patch clamping, I should mention that single channel data is essentially from a very small patch of cell membrane, which may contain hopefully one, or in this case, two channels, which can be either open or closed. It produces this type of waveform when it's sampled. So if I build that, you get this typical, this is the Gaussian we've got here. It shows how long it's spent. For instance, this is when all the channels are closed. This is when one of the channels is open, and this is when two channels are opened. And you'd probably want to go on and fit Gaussians to those. The cleanest of them. And the cursor. Sorry, analysis, fit data, and fit Gaussian between those cursors. And you'll notice that the fit actually fits the right hand, so the left hand edge of the bin, not the center of the bin. Maximum you want to take into consideration when you look at the mean of the Gaussian is actually not in the middle of the bin. The reason for that is that histograms in Signal are actually just a way of drawing the data. For instance, I could just change the draw mode on that. Draw mode. And that could be changed to line. And you can see if it's drawn differently, then it makes sense why it's fitting that way. Power spectrum. We're looking at the frequency contents of the data here. So we can specify which channel we want to analyze. We've got one here anyway. The FFT size, that's fast Fourier transform size. This has to be a power of 2 because of the way the algorithm works. And also the number of points in has to be smaller than the number of points you've got in the frame, otherwise it won't work. If you were only interested in a section of your data, then you could move an easier way to specify that is decide where that is in your data, and then you could apply that as an offset here. So then we'll just do the frequency content of the subsequent data. And this is because the sampling rate we've chosen. This happens to be the 256 FFT is at 256 milliseconds, worth of data from the offset. The way the Fourier transforms work is it assumes that the data repeats infinitely. That can cause discontinuities at the edges of the area that you're analyzing, which in turn will introduce new frequencies into the data. And the way to get around that is to multiply the waveform by a different shape that tends off to zero at the ends. So we get a new waveform, which is hopefully very similar to the original waveform, but tails off gradually to zero at the edges. That prevents that discontinuity and hence doesn't introduce new frequencies when you come to do your analysis. The function that you're using to multiply your original waveform by is called the windowing function. And there are a number of different windowing functions available in Signal. They all have their pluses, their pros and cons. Beyond the scope of this talk as to go into the details about them. But for most people, the Hamming function, which is a raised cosine, you make a simple cosine wave which has been raised by 1 so that it does tend off to 0 at the edges, and multiply the original waveform by that. And this is going to have a very strange spectrum, I'm sure. Yeah, the first bin of the spectrum is nearly always very high, and that's the DC component of your original waveform. And if I stretch that up a bit, you can see there are various other frequencies in here. Quite often there's a spike in the frequencies around either 50 or 60 hertz, which would be amazing to gain noise in your data. Leak subtraction. This is the voltage clamp method. If I data file with some voltage clamp data in, and what we notice is on the bottom trace here we've got the voltage stimulus, and on the top trace we've got the cells, the cell membrane current. And as the stimulus increases in height, eventually you reach a threshold and the cell responds. And if you're below the threshold, you don't get a response from the cell. And now if we assume that the cell membrane obeys Ohm's law, when the voltage activated channels are not responding, then we can work out basically a resistance curve for the data. So we can work out given a given height of stimulus pulse, exactly what response, what current trace we should expect if the cell hasn't responded. And having done that, then when the cell does respond, we can subtract the non-responding curve from the responding curve, and thus remove the leakage and the capacitive transient from the data. So that's the theory of how leak subtraction works. And if we go into the memory view, new leak subtraction, there are the various ways of specifying which frames don't have a response in them and which do. We start with the basic method, where we specify just basically which frames don't have responses in them. And the first frame in this file is 1, and the last is frame 5. Now, in order to work out, in order for this to work, the program needs to work out how high the stimulus pulse is. So you need to specify a time before the stimulus, which is your baseline, and you need to specify time during the stimulus so that you can make that measurement. And so a baseline time, we're going to put it in the middle of this area here. So that's about 4 milliseconds. And the pulse time we'll put right in the middle over here. It's about 40 milliseconds. Now we want this, if you want this measurement to be as accurate as possible, and this is quite clean data, but normally you'll have some noise on this. You want to average the noise out by making that measurement over a width. Currently it's set to 10 milliseconds. Now that, if we look at the data here, if we're measuring over a width of 10 milliseconds here, we run the risk of including some of the stimulus pulse when we make our baseline measurement. So we probably want to make that a little bit smaller. Bring it down to 8 milliseconds. Baseline correction, when we've done all this and subtracted out the theoretical trace from our original data, you'd probably want the baseline to be back at 0. Usually there's some sort of offset here which is crept in. The equipment you're using is applied some sort of offset when it's been amplified. You want to correct for that and put that back at 0. So when there's no stimulus, there's no current. So that's what that baseline correction will do. And again, we've got the count excluded frames. That's probably more important when we start doing what's called PN protocol, which I'll come on to in a moment. Again, if you have 5 frames that you want to use to form the leak with, what do you do if one of them happens to be tagged and therefore isn't being included in your analysis? Is that one of your 5 frames still? You probably do want to say that's one of your 5 frames, because otherwise you'll be using another frame which is potentially got a response in it and form your leak, which would make a nonsense of your calculations. So if I do new here, and again process all my frames, you see what we've left with is just the response from the voltage activated channels in the cell. And you know, the capacitive transient is all but gone. The leakage current is almost gone. It suggests it's not quite a linear relationship, but it's pretty close. So there's only a few frames in this leak subtracted data. So that's the basic leak subtraction. If we look again at other methods of specifying the frames, this PN protocol, the PN protocol is positive negative. So when you did your original sampling, you would have had perhaps a set of frames where you provided a negative square stimulus pulse, which you know would not have produced, would not have gone over threshold, so you would not have got a response from the cell. These tend to be done in cycles, so you have a number of negative pulses followed by another fixed number of positive ones, followed by another number of negatives, and you go around cyclically, keeping up with that. So you're refreshing your definition, your model of the leakage currents each time you have a set of negative pulses, and then applying that to the next set of pulses where you have a positive stimulus, and therefore a potential response from the cell. So this time instead of having a first and last frame, we have the number of negative pulses, the number of frames from which to form the leak, followed by how many subsequent frames you may get a cell response from. That's 7. So in a longer experiment, this file's only got 12 frames, I believe. In a longer experiment, it would cycle round and it would go back and again, after having subtracted from 7 frames, it would go back and form a new leak to then subsequently subtract from the next set of frames. And then this is where the count excluded frame becomes very important, because obviously that if your original sampling protocol only had 5 negative pulses followed by 7 positive ones, and you excluded one of the negative ones because it was tagged, for instance, then you wouldn't want it to take another frame just to make up the extra 5. You want it to count that as if it was really included. And the other method of specifying is to use states. So the chances are there will be certain states you use during sampling, a set of stimuli that you know wouldn't produce a response from the voltage activated channels, and you can specify what that state is in the dialog here. So whenever it comes across that state, it uses it to modify its definition of the leak. Interval histogram. We don't come across many of these in Signal, but what I can do is they do require a very busy marker channel with lots of markers on it to work well. If we look, for instance, at the actions file, which has action potentials in, I can generate some markers for this data. This is something that Simon was doing in the last talk. I create a new memory channel, and I import from channel 2 all the frames. Peaks of size 20 millivolts. Okay, so now I have a memory channel with all the markers in, showing where the action potentials are. Now, if I wanted to do a histogram of the intervals between these markers across all the frames in the file, I can do that. Go to the interval histogram. All channels off. Then there is only one channel that has markers in here. Across the full width of our data. And this is not going to be very spectacular because I don't have very many markers in my data, but hopefully it shows the principle. So we're going to have intervals up to 100 milliseconds, binned in such a way that only 1 millisecond bins. Use intervals across frame boundaries. It's possible to have a data that's sampled continuously. That's gap-free sampling. If you've done that, then you can include intervals across one frame to the next. And if I process those, you can see we've got quite a few intervals that are 8 to 9 milliseconds. The rest is dotted along various other intervals in our file. Okay, you may have noticed when you're doing your analysis that we have all these commands for buffers. The question is, what is a buffer? A buffer is an extra frame. It's not actually in the file, it's held in memory, and it's hidden, if you like, behind the file that you can see on the screen. And initially, it has just zeros in it. If you want to see what's in the buffer, we can say exchange buffer. And as you can see at the moment, there's nothing in it. Change back. So I can also perform various other operations. I can add something into the buffer, or I can subtract it. So for instance, if you wanted to subtract one frame of data in your file from another frame of data in your file, you could, let's, for instance, go back. I go back to one that hasn't got a response. If I put that in the buffer, and then I go to the next frame, I can say subtract buffer. It's just a way of, it's subtracted one frame from another by that method. Now this is modify the data in memory at the moment. And what happens if you try and move to the next frame, it asks, what do you want to do with this data that you've modified? Do you want to keep it in the file, or do you want to throw it away? This is one of the reasons we don't use the buffer a lot, because at this stage, if you were to save the changes, you would overwrite the data that's in the file, and it will be gone forever, and you won't get back to it. If you're going to play around with this, then you're probably best making a copy of the data first. But better still, there's usually another way of doing things without using the buffer. Discard. One thing I can do is build up an average of all the frames with various use of the buffer. We can say average into buffer. Again, and so on. And having done that, you can have an exchange buffer to see the average it's building up. Put that back again. And if I can append a frame to the file, so right we are, we've got a new frame 13 now, which is appending right at the end of the file. And I can exchange that with the buffer. So now I've got a copy of the buffer in my file. And I can write that into the file. And it hasn't overwritten any data in the file because it's appended at the end. So that's a little bit more convenient and safer. And it allows you then to overdraw the average with other frames in your file if you wanted to. There are more convenient ways to do this, though. I'll just undo that in a moment. Frame. I can build up an average using memory views. And let me just do a quick average in here. Right. And I wanted to put that into on the end of the file. Again, I could do a frame analysis end frame. I can go into this file, this view. Now I can do Control-C, copy that frame into memory, into the clipboard, and I can do Control-V, and it pastes it into the file. And that's Yes, I didn't copy. I didn't do an average here of the entire frame, which only did 40 milliseconds there. Let me try that again. Delete. To be 40 milliseconds. That was to be about 2000. That's more convincing. And then if I do pen frame on there, here, Control C to copy, and here, Control V. So, and if you have several files, you can move data between the files in this way by appending frame, copying and pasting data from one frame to another. You can average the whole frame with the memory view, yes. I specified 2000 because it was convenient there. The question from Sam, can you average the whole frame with memory view? Yes, you can. As you might have imagined, working with the buffer can be very tedious because you should step through each frame, decide whether you want to add it or not. There are this multiple frames option, which has all the options you have for the buffer and various other things you can do as well. And you can apply that operation to a set of frames, which speeds things up no end for you. There are various other useful things we can do with the multiple frames. One is, for instance, as you know, we can tag individual frames in this manner. Having gone through your file, having done that, you might decide you want all the tags removing, which could be very tedious to go through them all individually, looking for the tag frames and untagging them. The convenient way to do that is to do multiple frames. And one of the options down here is untag frame. You apply that to all the frames, and all the tags are gone. Another thing which can be very tedious to undo manually, if we've done a fit, for instance, do a fit here. And fit the data. And do a single exponential between cursor 1 and cursor 2 on channel 2. And do that for all frames. We've now got fits on all the frames. And if you didn't want them on all, you want to get rid of them, you can right click on them and do clear fit. But again, very tedious to go through the whole file doing that. So again, multiple frames and clear fits. And that clears them all in the file. We've got a couple of questions coming. Hannah, can you use this method using the buffer to subtract data of a virtual channel from one frame from another frame. Subtract the virtual channels are not part of the buffer. No, if the buffers are, you can't change channels with the buffers. You can't, no, the only way you could use data in a virtual channel, subtract data from one frame or another. But the way to get data in a channel, in a virtual channel, as being real data, is to use it to form an average. So you can you use the memory view and say, make an average. Waveform average, say, and then you could specify in here that you wanted a virtual channel as included in your average. And when it builds the average, it becomes real data that can be manipulated. Even then, it's not going to line up with the same channel in a different file. So a little bit more careful care needed there. So if that's something you want to do, then by all means, get in touch with me, and I'll get back to you in more detail. A question from Lasani. If you have responses across frames, is there a way to show all the responses superimposed in one frame in addition to generating the average response? All responses superimposed, yes, we can overdraw data. That's the one. Just say overdraw settings. There are all kinds of settings here for overdrawing, but or we could just say overdraw, and we're overdrawing all the frames on top of each other here. You can do it in a three-dimensional way so that they actually disappear off into the distance. If you appended the average, then the appended frame would be included in this this overdrawing method as well. And you can set the colors to use here. Gray's default. You can cycle the colors and all sorts to make it easier to visualize. We have channel arithmetic. Another thing we can do. Let me turn the overdrawing off a moment. So we can, if we select a channel, we can apply channel arithmetic to it. Zero the data, so that sets that channel to 0. Again, this is a very dangerous thing to do in terms that you're overwriting your data if you move to the next frame or close the file. You want to overwrite your data, or you want to discard changes you made. Virtual channels have largely been superseded by virtual channels. So the channel arithmetic has largely been superseded by virtual channels. And so there's various other things we can do here. Rectify and negate the data. 3-point smooth, 5-point smooth. Scale the data. Scaling the data is different to changing the scale factor on the data. Scaling data actually multiplies the data as it would be stored in the file, rather than just apply a different scaling factor. Apply offset, etc. Channel arithmetic has largely been superseded by virtual channels, though. It's a lot easier to see what you're doing with virtual channels without risking corrupting your raw data. But yes, you can divide one channel by another. If you wanted a channel which actually contained conductance, for instance, or resistance, you could divide one channel by another. But it's better to use virtual channels if you can. What I can do, I can show you some. We zoom in on the data. This you can see this area here has got a lot of mains interference sites. And if I try and smooth that, channel to smooth it. Shift 5 is probably this short keyboard. See that, it only goes so far. But what I can do is can then filter the data. Simon already talked about FIR filters. There's an IIR filter, which is infinite revoked response. These closely mimic some of the analog filters that you may be familiar with. If I try to apply a notch filter here, the resonator makes a good notch filter. Now, if you try to, this is the center of the frequency center, so I think this is American, so if we make that 60 hertz. If the Q value, that is the narrowness of the notch which you're trying to filter out, is too narrow, then you find it doesn't work. You need to ease off a bit on the Q value, or you can manipulate it here. It's very difficult to not to move the center when you're doing that, so it's better just to type it in. And you can see there it's largely got rid of the mains interference. And again, we have the problem now, do we want to overwrite our data? I'm not going to do that this time. Let's try it. I think it's discarded my changes already. But that's IR filters are a good way of cleaning up main noise, and they're probably more used in Spike 2 because of the downside of an IR filter is that when you apply one, if you've got a peak in your data, it moves, it shifts to a slightly later time. If we look again at virtual channels, this is something Simon did some demonstrations with virtual channels in the last talk. I'll create a new channel with, let's start with just a copy of the data in channel 2. Auto optimize. Save me having to do this every time I change the expression. So at the moment, the virtual channel just got a copy of channel 2 in it. Now you can imagine if I wanted to do this, perhaps this decaying exponential, if I wanted to remove that, and they have fitted something to it, do a fit. Okay, so channel 2. This is 1, 2, 2. Now you might want to subtract that fitted curve from the raw data. The way to do that is we can right click on it and we say copy fit for VC. That generates a virtual channel expression equivalent to that curve. So now if I do subtract, if I paste it into brackets, you can see now in the virtual channel, the data between the cursors then has gone to 0. So that's subtracted out the exponential decay from the raw data there. There are a whole host of other things we can do in virtual channels. One other thing that people quite often do in virtual channels is generate stimuli that they want to use as an arbitrary waveform output. So we can say generate waveform. Sinusoids are very commonly generated. Like that. So then you have a waveform which you could subsequently use as an output if you wanted to stimulate. Now, obviously, sine waves you can generate in the pulsive dialog anyway, but you can do other things with this. You can then apply apply an envelope to it. So then we can rise in a second, hold for 10 seconds, all times in milliseconds, sorry. So we can rise in 100 milliseconds, hold that for 1,000 milliseconds, and fall very quickly. Align that to 0. And you can see there the sinusoid now increases in amplitude gradually, then holds at a level, and then decreases very quickly back to 0. And just applied this envelope function to the sinusoid. Virtual channels are stored in the configuration file. So when we close the window and reopen it, the virtual channel will reappear. Other things we can do in virtual channels is we can use Boolean expressions, like a logic expression. For instance, if we wanted the waveform to go to 0, if a frame was tagged. So it's an untagged frame, but if I tag the frame with Control-T, the waveform goes to 0, because you can also use, for instance, if channel 2, this is an example, channel 2 is more than minus 10. Now that expression evaluates to 1 if channel 2 is more than minus 10, and to 0 if it's less than or equal to minus 10. So now the sinusoid is 0 most of the time. It doesn't go above the required level very often there. So let's get that a bit smaller. There we are. The sinusoid just disappears in areas where channel 2 is less than 50 milliseconds, 50 millivolts. So as you can see, there's lots and lots of other things we can do in virtual channels: rectifying, integrating, differentiating, smoothing. Again, this is from the channel arithmetic. If you do it here rather than using the channel arithmetic method, then you're not corrupting your original data. Remember Remember, you can also use if a frame number is less than n, then you have one expression. If it's not, then the virtual channel again goes to 0. You can do some quite powerful things using Boolean operators. So if you multiply by an expression that goes, that's 1 if it's true and 0 if it's false. And a little bit of time to talk about the voltage clamp stuff we can do. If we have notice your clamping tab, you specify whether you want wholesale current clamp, voltage clamp, or single channel voltage clamp. The channels you specify in here are checked. The units have to match correctly for you to be doing the appropriate type of clamping. And again, with the DAC, it has to be set up in advance so that you're stimulating in the correct units. Otherwise, when you come to run your experiment, it won't know how to analyze your data or give you measurements. I see Lasan is asking the very question here. There is a membrane test. Yes, we can. Lasan is asking, is there a membrane test equivalent in Signal to calculate access resistance and input resistance, etc., in voltage clamp? If you have the response of initial access to a current step during breaking, is there a way to analyze these parameters offline in Signal? We certainly do it online. Offline, I think is going to require a script. If it's something you need to do offline, then by all means get in touch. I'll find a way to do that for you. If I'm having set up the clamping that I'm doing, we'll get this dialog here. What the clamping bar appears when we actually sample, and you can see it's measuring the access resistance and the membrane resistance at the moment. If I click on this checkbox, I get the total resistance, which is probably what you want to do in setup. And if I click on the button, it's picked up the stimulus response, and it's fitted a curve to it. And when it can, unfortunately, exponentials are notoriously difficult to fit. It's holding in there now, and you see you get the various responses, various values: the total resistance, the access resistance, membrane resistance, and membrane capacitance, and the time constant. And then at the bottom here we have a scrolling display of the selected value being plotted for us. And if I adjust the capacitor, you can see the graph scrolls across and changes value down here. There is a whole other talk on voltage clamp, patch clamping, so don't worry if I'm going too fast here. I'm a little short on time. If I look at some single channel data again from just a small patch, remember this is single channels in a patch of membrane. If I wanted to create an idealized trace showing where it was open, closed, and at what level it was open, I can, easiest to put some horizontal cursors on here. And I'll put 3 on to start with. A bit. Okay, so I put a cursor here roughly on the closed level, and I put 2 thresholds in. One is for a threshold it needs to cross in order to open, and the other one is for threshold it needs to cross in order to close again. The reason for having 2 separate thresholds is it makes you more immune to a lot of noise on your data. Very noisy data, then putting a single threshold on is very tricky. And if I go to analysis, open close times, new idealized trace analysis, new idealized trace threshold, and we can say open to the base level is cursor 1, and open above cursor 3, right there, close below cursor 2. Transition points is the number of points after it crosses the threshold before you start looking for another threshold crossing. If it's very heavily filtered data, the crossings might not be very steep, and they could be tailed off at an angle. You don't want the noise causing multiple threshold crossings, so you want to wait a number of points before you start looking for another one. Interpolation, it might not cross exactly on a data point. You might, when it does cross, you might try to work out exactly where it is between the 2 points that the crossing occurred. And baseline track, when it's in a closed state, it will track whether or not that closed state is drifting, and move all the thresholds relative to the baseline as it moves through your data. Multiple levels, so you've got more than one channel in the patch. So I'm going to allow multiple levels, so you can find the ones up here as well. It takes the mean value between the 2 thresholds and triples it to find the threshold for the next level. And it's an outward current, so we're actually at the closed state at the bottom. Closed state is 0, and then the more positive result values correspond to openings. And when I process that, I get an idealized trace, which we can subsequently analyze, and there will be a lot more detail on how to do that in the next talk. We do have another analysis, other methods of forming the idealized trace. The scan analysis, in particular, is very powerful. It's developed by David Cahoon, and copes very well with subconduction levels and filtered data. In order to make that to work, I would have to just open a different file. Zooming in on that. What I'll do initially, you need to tell it, give it an area baseline to work with. Baseline measurements. So over the visible area, it makes a few baseline measurements. And then we can start putting cursors up again. Again, we'll tell it where the open level is, where the baseline is, and another threshold. This time it's just a threshold for detecting that something's happened. Looking at this data, there's a short closing here, which is too short to meet. If you just use a simple threshold crossing, it wouldn't meet the threshold, so it will go undetected. The scan analysis can actually can pick that up And there'll be there's lots of scope for an hour's talk on how to do this sort of thing coming up in a few weeks' time, if that's something you're interested in. Okay, well, so we'll take some more questions if anybody has any. Next session is going to be advanced sampling. Which will go into multiple states, so various differing types of stimuli you can have, and you can change between which stimuli you use and the order in which you want to use them. Okay, we got a question. In a virtual channel, can I subtract the first frame through all frames in the channel? Now, a virtual channel is calculated from data in the current frame. It doesn't cross frame boundaries. If you want to subtract the first frame from all subsequent frames in the channel, you may be able to do that with you might be able to do that using a buffer. If we, for instance, let's go back to the first frame of the file. We add that to the buffer, and then do multiple frames and subtract buffer data from the frame data across frames 1 to 12, I think it is. That will do that will subtract the first frame from all subsequent frames in the file. It's not something you do using virtual channel. You can do it using a buffer. It's destructive to your original data, so be wary about that. And you might want to take a copy of your data just in case you get it wrong. Hopefully that's answered your question. Okay, well, thank you for everyone for coming, and we'll call you a day there. Hopefully see you in another session soon.